Greetings, everybody. Learning is a hobby here. Um, as promised, although it's a little bit late, uh, I wanted to post a video on the summary for Appendix 3 and Chapter 4 for Spivak. So that's what I'm going to do here. I apologize for, I know I said I was going to do this last weekend, but I think as I mentioned in my last video, if I don't know if you live in New York City, it's been unseasonably warm this weekend. The trees are blooming, and I have terrible seasonal allergies, so I just was not in the mood to make videos in that state. Hopefully this weekend it'll be a little bit better, so I can get through some other videos. But anyway, that's not really your problem. So I want to get through the summary for the summary for Appendix 3 and Chapter 4, and then either tomorrow or the day after I'll get to the exercise set. So let's not waste any more time. Let's start on the summary for Appendix 3. Now, I'm not going to go in detail into some of the stuff that he talks about in Chapter 3. In Appendix 3, and I'll tell you why. It's because we've already gone over the basics of polar coordinates in both the Taylor book and also in the Simmons book. So I'm going to just sort of, breeze through the introductory stuff here on polar coordinates. The whole the whole Appendix 3 here is on polar coordinates. So just very briefly, if you remember, polar coordinates are another way of representing points in the plane. Instead of using the intersection of a vertical and a horizontal line to pick out the geometric point, you use a ray that makes a certain angle, that has a certain length, that makes a certain angle with what's called the polar axis, and the pole is the point where the rays emanate from. So, and then you have equations that let you go back and forth between polar and Cartesian coordinates, which are these. Again, I won't go into that in detail because I've already done that in other videos. All right. He talked about this definition here. Again, there's really only one thing that I want to spend any amount of time on in this section, so I'll just breeze through this stuff relatively quick. So the definition says, if f is a function, the graph of f in polar coordinates is a collection of all points p with polar coordinates r comma theta, satisfying r equals f of theta, or in other words, the graph of f in polar coordinates, which I'm calling gamma here, is a set of ordered pairs f of theta comma theta, where theta is an element from some subset of the real numbers. Here I'm assuming that we're measuring theta in radians, which hopefully shouldn't be surprising. Okay. He also asks us to graph this polar curve here, r equals cosine theta. I'll just describe real quickly how I graph polar curves, and then I want to move on to sort of like the big thing that I want to talk about in this section. So the way that I like to do this is I like to graph the function in rectangular coordinates first. So the vertical axis here, let me get my marker out. What color should I use? Maybe I'll use purple. That might stick out better from all the other colors that I have on here. The vertical axis I'm calling r, and the horizontal axis I'm calling theta. So if you graph this curve, and I'm only graphing it from 0 to pi. The reason for that is you get the whole polar graph by just doing a half period of the cosine curve. So this is what the graph of cosine looks like. Hopefully you remember from pre-calculus. Over 1/2 of its period. And you can use this to get the graph of the polar curve. So for example, at 0 radians, which is, that angle there, the radius is 1. So here, notice I'm starting at a radius of 1. And then as you go from 0 to pi over 2, in other words, this range of angles here, the radius decreases from 1 down to 0. So that's why the curve goes like this. Right, that's why I have the arrow pointing this way. It starts at on the polar axis, and it curves toward the pole as theta goes from 0 to pi over 2. And then from pi over 2 to pi, the radii become negative, and they increase in magnitude from 0 to 1. The angles from pi over 2 to pi is this range here, but notice that the radii are negative. So instead of graphing, for example, the point here, you would graph it in the opposite quadrant. So it goes over here. So when you graph this branch of the curve here, you just get the bottom half of this circle, and it gets traced out in that direction. And as you increase the value of theta, it just repeats over and over again. It just keeps tracing over that circle. So that's what the graph of that curve looks like. All right. And then, and also he wanted us to write the Cartesian coordinates of that function. So just using the formulas to go from polar to Cartesian coordinates. If I multiply this equation, both sides of this equation by r, you get this, and r squared is defined to be x squared plus y squared, and r cosine theta is x. Okay, and if you remember, that's the equation of a circle, so everything matches up here. Okay, so this is the big thing I want to basically spend the time on in this appendix, which is he derives the equation of an ellipse in polar coordinates. So let's do that. So if you look at the picture here, I have a badly drawn ellipse. Just pretend that looks like a symmetric, nice smooth ellipse there. The point XY is a point on the ellipse, and the point F and O are the foci. Notice that I have one of the foci at the pole, and the other foci has has Cartesian coordinates, -2 epsilon a comma 0. I'm calling that F, and the polar radius here is this one. Oops, this one here, and I'm calling that R. And we're assuming that this ellipse has, the sum of the distance from one foci to the point. If you add both of those distances up, you get 2a. That's an assumption, which means that if this length here is r, this length has to be 2a minus r, right? And just another note here, we have that note. So here, if you look at the x coordinate of the other foci, the other focus, -2 epsilon a, we know that epsilon has to be between 0 and 1, since the distance, the 2a is greater than the distance from between the two foci. So in other words, this distance here is purple. I don't know if purple works so good. Let me use red here. So this, obviously this distance here is less than this distance here, and this point here has to have x coordinate less than -2a as well, right? So this distance is some number between 0 and 1, multiple of -2a, right? Because this distance here is 2a. Okay. So just continuing down here. So r squared, just by definition, is x squared plus y squared, and also 2a minus r squared, just by definition. If you look at the picture, oops, hopefully that notification didn't show up on Zoom, but it doesn't really matter. 2a minus r squared is the distance from the focus F to the point P squared. But that's also by the distance formula given by x minus -2 epsilon a squared plus y squared, right? You just take the difference between the x coordinate. Let me just show that here. Take the difference between the x coordinates here squared minus the distance between the y coordinates squared, and add those together, and that gives you this distance squared, right? Which is this number squared, all right? And then just multiplying everything out and combining like terms, you get this expression that the arrow is pointing to. And if I subtract r squared from the left-hand side, and which is equal to x squared plus y squared, and I subtract that from the right-hand side, we get the equation 4a squared minus 4ar equals 4 epsilon ax plus 4 epsilon squared a squared. We can factor out a 4a on both sides and cancel them because a is not 0. And that gives us a minus r is epsilon x plus epsilon squared a, and now we can solve for r in terms of x. So r is equal to 1 minus epsilon squared a minus epsilon x. Okay. And we can just call that number 1 minus epsilon squared a, where he calls it capital lambda, so that's what I'm calling it. Then r is lambda minus epsilon x, so he calls that equation 3 because he refers back to it in this section and also in the homework, in the not the homework, the exercise set that we'll do in the next video. All right, and then just substituting x equals r cosine theta in for x, we get this, and that allows us to solve for r in terms of lambda, epsilon, and theta. All right, so this is equation 4. Again, he's giving it a name because we'll refer back to it later on. All right, so this is an important formula here. This is the polar representation of the ellipse. And just as a reminder, lambda and epsilon are fixed constants here that actually affect the shape of the graph. So, affects how eccentric the ellipse is, and it also affects how big the ellipse is. All right. And then so maybe I should say that's the first thing. That's the equation of the ellipse in polar, the equation of the ellipse in polar coordinates. That's the first thing we wanted to do. Okay, also from the chapter, which I did a long time ago, so if you've forgotten what we did in chapter 4, you can take a look back at that video. From chapter 4, we derived this equation for an ellipse, x squared over a squared plus y squared over b squared equals 1. This is in Cartesian coordinates and it's the equation of an ellipse where the sum of the distances between a point on the ellipse and the foci is defined to be 2a, and the ellipse is centered at the origin. So in other words, the semi-major axis has length 2a, the semi-minor axis has length 2b, and the foci happen at points negative c comma 0 and c0 in Cartesian coordinates, which means that b is equal to square root a squared minus c squared. The distance between the two foci has distance 2a. I'm sorry, not 2a, 2c rather. And just to relate that ellipse to the figure that we talked about a minute ago, let me just go back to that picture. So to get the same ellipse as we have here, what we would need to do is translate the ellipse with equation in Cartesian coordinates that I showed below. We have to translate this way by c units to the left, and if we choose c to be epsilon a, then we get this exact ellipse that we have here, right? Because the distance, remember, here is the distance here is I keep writing 2a. The distance here is 2c, which means that this point here, if we choose c to be epsilon a, will be negative 2 epsilon a. So it's the exact ellipse if we do that. All right, and using that fact, okay, so here I'm just saying what I just mentioned a minute ago. Using the fact that we're taking c to be epsilon or epsilon a, you can solve for epsilon by dividing by a because it's not 0. So epsilon is equal to c over a, which is called the eccentricity of the ellipse. And of course, he's mentioning equation 3 determines the value of lambda. So lambda equals 1 minus epsilon squared a. And using that, we can solve for a in terms of lambda and epsilon. So we get that a is, I probably should have circled these, but a is equal to lambda over 1 minus epsilon squared. Okay, and then also we can write b in terms of lambda and epsilon. So b we know is the square root of a squared minus c squared, but we know that c is epsilon a, so that's the same thing as a squared minus epsilon squared a squared, which is, when you factor everything out, equal to a times square root of 1 minus epsilon squared. Right, and then just rationalizing the numerator, we get that b is equal to a times 1 minus epsilon squared, which is, if you recall, that's equal to lambda divided by square root 1 minus epsilon squared. So we get that b is equal to this. I probably should have circle these formulas, but anyway, we can see there that the value of a and b, which determine the length of the semi-major and semi-minor axes, are functions of lambda and epsilon. right? So the values of lambda and epsilon tell you pretty much everything you need to know about the ellipse. Okay. And then just again, rewriting some things here. Epsilon is we showed was equal to C over A. Which C we know is square root A squared minus B squared, and then bringing the A underneath the radical means you have to square it, and then just simplifying things, you get square root of 1 minus B squared over A squared, so, which tells us that the eccentricity E, like I said, I actually said this a minute ago, but I'll just restate it. The eccentricity epsilon determines the shape of the ellipse, while lambda determines how big it is. All right, so that's basically the appendix for appendix 3 for chapter 4. So we're almost done with finally with chapter 4. I just have to get through the exercises. I started on them, but I haven't finished them yet. So hopefully either, I don't know, maybe tomorrow or sometime on the weekend, I'll be able to post that last video on chapter 4, and then finally we'll be able to move on to chapter 5, which is where the calculus material finally starts in the Spivak book. So we got that happening. I want to do chapter 2 in Taylor next, and I really got to get around to finishing chapter 1 in Schifrin. I know it's been months since I've done anything in Schifrin. I really got to get around to finishing that, so I'll make a push to finish chapter 1 in Schifrin. And there's one section left that we got to get through in the Simmons book, and then we'll, again, we're going to keep moving on, but steadily and slowly. So we're almost done with chapter 4. It feels like it's been a long time, but we're almost there. So again, thank you guys for watching. Hope you enjoyed this video and you got something out of it. If you have any comments or questions, leave them in the comments section. Please do like and subscribe. It helps the channel grow and get this content to people, like-minded people like you and myself. And I'll see you guys in the next video. So until that time, keep learning, everyone.